Hi everyone, I am Sam. Today we are going to talk about chemistry. Imagine for a moment that you're standing at a bustling outdoor market. It's early morning and the air is crisp. All around you, merchants arrange their goods: fresh fruits and vegetables, handmade soaps, old copper pots and pans. Each item at its core is composed of countless tiny building blocks, unimaginably small pieces of matter that make up everything you can see, taste, smell, and touch. You can't see these individual building blocks with the naked eye, of course, but they're there. This hidden world, filled with invisible particles and mysterious transformations, is the realm of chemistry. Chemistry might seem complicated or even intimidating, but if we peel back the layers of complexity, it begins to feel more like an adventure, one that spans centuries and continents. From the earliest attempts to understand the nature of fire and metals, to the elegant modern frameworks that describe how atoms and molecules behave, chemistry offers a window into how our world works at its most fundamental level. To get a sense of how humans first stumbled into the chemistry story, we can start in ancient times. Long before we had laboratories, textbooks, or even the word chemistry, people experimented with matter every day, often without fully realizing it. Early artisans and metalworkers learned how to extract metals from rocky ores and smelt them into tools. Potters discovered how to harden clay into ceramics by applying just the right amount of heat. Dyers found that certain plants yielded vivid colors that could stain cloth. And brewers understood that letting fruits and grains ferment would produce unique beverages. All of these activities involved chemical reactions, even if no one at the time understood what was happening on an atomic level. In these pre-scientific eras, attempts to explain these transformations often drifted into the mystical or the religious. The practice known as alchemy, which thrived in various cultures, including ancient China, the Islamic world, and medieval Europe, focused on seeking hidden truths in substances. Alchemists sought the fabled philosopher's stone, an elusive object believed capable of turning ordinary metals like lead into gold and granting eternal life. While these goals seem fanciful today, the alchemists were not merely dreamers. They were also meticulous observers who discovered new compounds, developed experimental methods, and left a legacy of curiosity. Alchemy helped lay the groundwork for a more structured, rational approach to matter, inching humanity closer to the science we now know as chemistry. But to truly understand chemistry as we do today, we have to journey into the 18th century and meet a man sometimes called the father of modern chemistry, Antoine Lavoisier. Lavoisier lived in a time when the field was still tangled up in old notions. Chief among them, the idea of phlogiston, a supposed invisible element released during combustion, burning. According to this theory, when you burned a piece of wood, it would lose phlogiston to the air. Metals that rusted were said to be releasing phlogiston slowly. This idea fit some observations, but failed to explain everything fully. It was more of a guess than a verified truth. Lavoisier had a remarkable mind, keen observation skills, and a willingness to challenge accepted wisdom. Through a series of careful and quantitative experiments, he showed that combustion and rusting were not about a mysterious phlogiston escaping, but rather about a substance in the air combining with other materials. In particular, he identified that air was not a single substance, but a mixture. Most crucially, about 1/5 of the air was a gas that caused things to burn and metals to rust. We now call that gas oxygen. With the discovery and understanding of oxygen, Lavoisier overturned centuries of flawed thinking. He devised a more systematic way to name chemical substances, placing a strong emphasis on consistency and logic. By putting chemical research on a solid, rational footing, he helped shift chemistry from a patchwork of guesses and traditions into a more exact science. Unfortunately, Lavoisier's life ended tragically during the French Revolution. He was executed in 1794, but his influence on chemistry would live on, guiding scientists for generations to come. Now, Lavoisier's discoveries were just one part of a much larger puzzle. The world around us, everything from the breath in our lungs to the metal in a spoon, can be broken down into substances called elements. An element is a pure substance that cannot be simplified further by ordinary chemical means. By Lavoisier's time, several elements had been identified, but they were known in no particular order or pattern. It was like having a drawer full of puzzle pieces, but no picture on the box to guide you. This is where another giant of chemistry enters the story: Dmitri Mendeleev. In the mid-19th century, scientists knew of about 60 elements: copper, iron, gold, oxygen, nitrogen, and so forth, but nobody had a good system for organizing them. Mendeleev, a Russian chemist, took on the enormous task of sorting these elements into a table. He wrote down each element on a card along with its properties, like weight, how it reacted with other elements, and its physical characteristics. After many attempts, something extraordinary emerged. When elements are arranged in order of their increasing atomic weight, as it was understood at the time, certain types of elements appear at regular intervals. Metals with similar characteristics lined up. Gases with similar reactions fell into place. A pattern was taking shape. Mendeleev's genius was not only in recognizing this pattern, but in trusting it so completely that he left gaps where known element existed. He predicted that new elements would be discovered to fill those gaps, and he even described their likely properties. When these predicted elements, like gallium and scandium, were eventually found and matched his predictions almost perfectly, Mendeleev's periodic table became one of the crowning achievements of science. Today, the periodic table is arranged not by atomic weight, but by atomic number, the number of protons in the element's atoms, which turned out to be the deeper foundation of the pattern. But the spirit of Mendeleev's insight remains at the heart of how we understand and navigate the vast landscape of elements. As we travel through chemistry's timeline, we see not just individuals, but entire communities of scientists refining the concepts. Lavoisier introduced the idea that matter is neither created nor destroyed in chemical reactions, only transformed. This concept, the law of conservation of mass, revolutionized how we think about matter and its rearrangements. Later, scientists like John Dalton pushed these insights further, proposing that elements are made of tiny, indivisible particles called atoms. Dalton helped define atoms as the basic units of chemical elements, and he argued that all atoms of a given element are identical in mass and properties. While we now know atoms are divisible into protons, neutrons, and electrons, Dalton's atomic theory provided a sturdy framework at a crucial time. As the 19th century progressed, the hunt for the atom's internal structure intensified. Scientists like J.J. Thomson discovered the electron, demonstrating that atoms had smaller subparts. Ernest Rutherford probed the atom's internal structure further, revealing a tiny, dense nucleus at its center. Niels Bohr refined our understanding of how electrons move around this nucleus. All of these developments steered chemistry from a field that once argued over imaginary substances toward a deeper understanding of the quantum nature of matter. Yet, for all these grand discoveries, chemistry is not just about lofty theories or chalkboard equations. It's also about practical applications and the human stories behind them. Consider the discovery of oxygen that Lavoisier clarified. Another scientist, Joseph Priestley, had managed to isolate this gas before Lavoisier's breakthrough. Priestley called it dephlogisticated air, thinking in terms of the old phlogiston theory. Carl Wilhelm Scheele, a Swedish chemist, also discovered the gas around the same time. These overlapping discoveries remind us that chemistry is often a team sport played across decades and continents. Knowledge is built gradually, piece by piece, and multiple people often arrive at similar conclusions independently. This teamwork extends even further when we think about how chemistry affects our daily lives. The foods we cook, the medicines we take, the fuels that power our cars, all of these things rely on chemical knowledge. In the kitchen, a simple act like baking bread involves yeast consuming sugars and releasing carbon dioxide bubbles that make the dough rise. In medicine, understanding how certain molecules interact with our bodies leads to treatments that can save or improve lives. In materials science, chemists design plastics, alloys, and composites that make vehicles lighter, buildings stronger, and gadgets more efficient. Let's return to the invisible building blocks that make up everything. Atoms are each defined by their number of protons, which dictates their identity as an element. Hydrogen has 1 proton, helium has 2, lithium has 3, and so on. Surrounding the nucleus of protons, and typically an equal number of neutrons, except for isotopes, are electrons, whirling in regions of space we call orbitals. The arrangements of these electrons determine how atoms bond with one another to form molecules. A molecule is simply a collection of atoms bonded together, like letters forming a word. Water, for instance, is a molecule made of 2 hydrogen atoms and 1 oxygen atom, H2O. Carbon dioxide, CO2, has one carbon atom linked to two oxygens. The variety of molecules that can form is staggering and underpins the diversity of substances we encounter daily. This connection between atomic structure and chemical behavior is another key breakthrough in understanding matter. In the early 20th century, scientists discovered that the arrangement of electrons in an atom follows certain rules, quantum rules. Electrons occupy distinct shells or energy levels. The outermost electrons, called valence electrons, determine how an element reacts with others. Elements that share similar electron configurations end up having similar chemical properties, which is why Mendeleev's pattern was so profound. It was a reflection of a deeper quantum reality, even though Mendeleev himself had no knowledge of quantum mechanics at the time. Quantum mechanics may sound intimidating, but its presence in chemistry is essential for explaining the finer details of chemical bonding and reactivity. Don't worry if it feels a bit abstract. Chemistry, after all, deals with phenomena that lie beneath what our senses can directly perceive. The beauty of the subject is that we can still make sense of it through experiments, observations, and well-tested theories, even if we can't see atoms directly. We've talked about the building blocks and their history, but what about the grand narrative of chemistry itself? Think of chemistry as a bridge between physics and biology. Physics sets the fundamental rules for how particles interact, while biology studies complex living organisms. Chemistry sits in the middle, explaining how simple particles assemble into complex structures that are alive, reactive, growing, and evolving. Understanding chemistry helps us appreciate the delicate balance in a plant's leaf as it turns sunlight and carbon dioxide into the sugars that feed the entire food chain. It also helps us understand how synthetic fertilizers boost crop yields, how pharmaceuticals can target specific pathways in our cells, and how advanced materials can store energy more efficiently. Throughout history, chemistry has always danced between the theoretical and the practical. On one hand, chemists want to understand why something happens at a fundamental level. On the other, they want to use this knowledge to solve real-world problems. Consider the Haber-Bosch process, developed in the early 20th century. This method allowed the synthesis of ammonia from nitrogen and hydrogen, providing a way to mass-produce fertilizers. This single chemical breakthrough drastically increased food production and changed the course of human history. Or think about the development of new materials. The silicon chips in our computers, the special polymers in medical devices, the tailored molecules that help batteries store more energy. These breakthroughs all depend on a deep understanding of how atoms and molecules behave and can be manipulated. And let's not forget the environmental challenges we face. Chemistry can help us understand pollution, how certain molecules affect air, water, and soil quality. It helps us find ways to clean up oil spills, reduce greenhouse gas emissions, and develop renewable sources of energy. It also guides research into capturing carbon from the atmosphere or designing materials that break down more readily, leading to less plastic waste in our oceans. Chemistry, in this way, is both a lens to see our problems clearly and a toolbox to help fix them. In the modern age, the tools of chemistry have become ever more powerful. We have spectroscopy techniques that allow us to deduce the structure of complex molecules by studying how they interact with different types of light. We have analytical instruments that can detect trace amounts of chemicals in a sample, equivalent to a single drop in an Olympic-sized swimming pool. We can cool matter down to near absolute zero to see how it behaves, or slam molecules together at high speeds to watch them break and rearrange. Computers and simulation software let us model chemical reactions and predict the behavior of new compounds before we even synthesize them in the lab. In education, chemistry provides a language of concepts that empower people to ask better questions about the world. Why does salt melt ice on roads in the winter? Why does cutting an apple and leaving it out turn it brown? What happens when you set a log on fire? Once you dip your toe into chemistry's waters, you start seeing it everywhere. Paintings fade over time because of chemical reactions in their pigments. Old statues turn green because copper reacts with air to form verdigris. The fizzing in a carbonated beverage is carbon dioxide escaping after the bottle is opened. Even emotions and memories have chemical underpinnings. Neurons communicate through chemical messengers, and what we call thinking is really a cascade of molecular events inside the brain. If we look back again to Lavoisier and Mendeleev, we can appreciate how far we've come. Lavoisier introduced rigor and careful measurement into chemistry, insisting that we weigh and measure substances before and after reactions to ensure our theories matched reality. Mendeleev gave us a framework to see order in what once seemed like a chaotic collection of elements. Together, they created stepping stones for later scientists to cross from an age of speculation into an era of understanding. The discovery of oxygen not only shattered old theories, it also taught chemists to trust experimentation over tradition. The periodic table gave structure to the entire discipline, allowing chemists to predict properties of elements and envision compounds that might not even exist yet. With each major discovery, from identifying electrons to unraveling the mysteries of quantum mechanics, chemistry became more refined, more powerful, and more capable of explaining natural phenomena. In a sense, learning about chemistry is like learning a new language. The alphabet is made of elements. The rules of grammar are the laws of how atoms bond and interact. Words and sentences form as we combine elements to create molecules and reactions. With fluency in this language, we can read nature's texts, understanding what gives a ruby its red color, why certain metals corrode, or how the human body converts dinner into the energy that keeps us alive. We can also write new stories, inventing materials that never existed before, crafting medicines that cure diseases, and devising cleaner energy sources that don't harm our planet. As we continue into the 21st century and beyond, chemistry remains a vibrant field, constantly evolving with new techniques and new challenges. Just as Lavoisier and Mendeleev could never have imagined the powerful particle accelerators or laser spectrometers we use today, we can only guess at the tools and discoveries future chemists will have at their disposal. Perhaps they'll find new ways to store solar energy cheaply, or create biodegradable plastics that break down harmlessly. Maybe they'll develop synthetic life forms with novel metabolic pathways, or engineer molecular machines that can build complex structures atom by atom. What's certain is that chemistry will continue to shape our world, helping us understand the materials we use, the energy we need, and the ecosystems we depend on. From the ancient artisans who unknowingly laid the groundwork to the alchemists seeking immortality and gold, from Lavoisier's careful experiments that revealed oxygen's role to Mendeleev's periodic insight that organized the elements, chemistry's story is one of human curiosity, creativity, and perseverance. That's all for today, and I'll see you in the next episode.